Today we are going to learn about Understanding GAN Architectures, a beginner's guide. We will explore the core architectures of GANs, differentiate between them, and understand their specific applications. Welcome to our beginner's guide on Understanding GAN Architectures. In this video, we'll explore the fascinating world of Generative Adversarial Networks. GANs are a class of machine learning frameworks designed by Ian Goodfellow and his colleagues in 2014. They consist of two neural networks, the generator and the discriminator, which work in opposition to generate realistic data. Understanding these architectures is crucial for those looking to develop AI models that can mimic the complexity and depth of real-world data.
At the heart of a GAN are two main components, the generator and the discriminator. The generator's role is to produce new data instances that resemble the training data, essentially acting as a forger. On the other hand, the discriminator serves as the detective, evaluating the authenticity of the data provided by the generator, distinguishing between real and fake data. This creates an adversarial process where the generator tries to improve its data to fool the discriminator, while the discriminator enhances its detection capabilities. This back and forth continues until the generator produces data indistinguishable from reality, illustrating a dynamic feedback loop where both networks are simultaneously trained. The adversarial process in GANs is akin to a competitive game between the two components. This zero-sum game involves the generator improving its synthetic data to deceive the discriminator, while the discriminator refines its ability to discern real from fake data. The goal is to reach a point of convergence where the generator's outputs are so realistic that the discriminator can no longer differentiate them from real data. This state is an example of Nash Equilibrium, where neither player can improve their position given the strategy of the other. Achieving this balance is crucial for effective GAN training and results in the creation of highly realistic data models. As the field of GANs has evolved, several architectures have been developed, each with unique features and applications. From the original GAN model, researchers have expanded into specialized architectures like GANs, CycleGANs, and more. These variations offer distinct approaches to improving data generation and tackling specific challenges. Understanding the nuances of each architecture is critical for selecting the right model for particular tasks. In this segment, we'll delve into the characteristics that differentiate these architectures, providing a foundation for selecting the most appropriate GAN model for your needs. Deep Convolutional GANs, or DCGANs, represent a significant advancement in GAN architecture. By incorporating convolutional layers, DCGANs enhance the model's ability to generate high-quality images. The convolutional layers enable the network to capture spatial hierarchies and patterns, making DCGANs particularly effective for image-related tasks. Their architectural design has made them a popular choice in research and practical applications, such as art generation and image super-resolution. As we explore DCGANs further, you'll see how their structure contributes to improved performance in generating realistic images.
CycleGANs are a breakthrough in the field of image-to-image translation. Unlike traditional GANs, which focus on generating new data, CycleGANs excel at transforming images from one domain to another without paired examples. This is achieved through a unique training technique that involves a cycle consistency loss, ensuring that an image translated to a new domain and back retains its original form. CycleGANs perform bidirectional training between domains, making them ideal for applications like style transfer and object transfiguration. Their ability to work with unpaired data opens up new possibilities in various fields, from art to medical imaging.
Understanding the key differences between various GAN architectures is essential for selecting the right model for your needs. While DCGANs focus on utilizing convolutional layers for enhanced image generation, CycleGANs specialize in domain translation without paired data. These architectural distinctions lead to different practical applications and training methodologies. While some GANs excel in generating realistic imagery, others are designed for specific tasks like translating styles or enhancing resolutions. By comparing these architectures, we can better understand their strengths and limitations, enabling us to make informed decisions when choosing a GAN for specific projects.
The practical applications of GANs are vast and varied, spanning numerous industries and use cases. In the creative sector, GANs are used for generating art, music, and even realistic virtual environments. In healthcare, they assist in creating synthetic medical images for research and training purposes, aiding in data augmentation where real data is scarce. GANs also play a crucial role in AI-driven art, producing innovative pieces that challenge traditional notions of creativity. By understanding these applications, we can appreciate the transformative impact of GANs on different fields and the potential they hold for future advancements.
Training GANs presents several challenges that can hinder model performance. Instability during training is a common issue, often resulting from the adversarial nature of the networks. Mode collapse, where the generator produces limited diversity in outputs, is another frequent problem. Achieving convergence between the generator and discriminator is critical yet difficult, requiring a delicate balance between the two. Addressing these challenges involves exploring various training techniques, such as using alternative loss functions or employing regularization methods. By understanding these obstacles and potential solutions, we can improve GAN training outcomes and achieve more reliable models.
Choosing the right GAN architecture involves evaluating several factors to ensure optimal performance. Start by identifying the specific requirements of your task, such as the type of data and desired outcomes. Consider the availability and quality of your data, as some architectures perform better with extensive datasets. Evaluate your computational resources, as more complex architectures may require significant processing power. Understanding the trade-offs associated with each architecture, such as model complexity versus performance, will guide your decision-making process. By carefully considering these aspects, you can select a GAN model that aligns with your project goals and resource constraints.
The field of GANs is constantly evolving, with new trends emerging in research and development. Recent advancements include novel architectures that address existing limitations, such as improved stability and diversity in output generation. Researchers are also exploring innovative training techniques to enhance model performance. As GANs become more prevalent, ethical considerations regarding their use and potential misuse, such as generating deepfakes, are gaining attention. Looking ahead, we can expect further breakthroughs in GAN technology, driven by ongoing research and the growing demand for realistic data generation in various applications.
Thank you for joining us on this journey through the world of GAN architectures. We've explored the core components, various architectures, and their practical applications. GANs have revolutionized data generation, offering unprecedented opportunities across multiple fields. We encourage you to continue exploring this fascinating area, as the potential for future innovation is immense. As the technology evolves, the applications and implications of GANs will only grow, making them an essential tool in the AI landscape. Thank you for watching, and we hope you found this guide both informative and inspiring.